In this module, we're going to learn about analyzing water flow through porous material. This will involve several blocks of information, and we'll start off by looking at the properties that are going to be important to doing this kind of analysis. In particular, the storage and transmission properties of porous media. We'll move on to processes during flow and change in storage, develop some equations, solve them, and then look at applications. That'll take us through the next several classes. So today we'll look at the storage and transmission properties. Well, in particular, just the storage properties. The most important property will be porosity, and there are several different types of porosity that we need to be concerned with. The most basic type of porosity is the total porosity, and that's defined as the ratio of the volume of voids in the porous material to the total volume. So if we've got a block of material that looks like this, here's some grains, then this is the material between the grains, that's the voids, that volume to the total volume of the material shown there, that would be the total porosity. There will be primary porosity that's formed when the rock is formed, and then the porosity changes through various geologic processes. That would be secondary porosity. We'll look at typical values of porosity, and then other terms that are related to storage that are somewhat related to porosity, but since we've defined porosity here, these will be terms that have a different definition than this. And here are some of the important ones: the volumetric water content, degree of saturation, specific yield, and retention. And then we'll also look at a porosity that's related to the flow. This is called the effective porosity. This relates the flux to the average velocity through porous media. So that's an overview. Now, if we want to store water and rock, then the porosity, I think, is going to be an important component of understanding this. It's defined here: volume of voids to the volume of total. And when the material is saturated, then this volume will be filled with water. You can see here that the geometry of these voids takes on a variety of different, fairly complicated shapes. So the voids are these spaces here in between these grains. In this example, these are fairly idealized, fairly rounded grains of sand. But porosity can also have different shapes. Here's some fractures in this rock, and these would be voids that would also constitute this volume when we're taking that ratio. And we might also enlarge the pores. These are these examples shown here and here are pores that would be on the millimeter scale or perhaps smaller. But it's also possible to have pores that are much larger than this. And here's an example. You see that guy in there in this cavity that's probably a fracture that's dissolved out in limestone. So the pores can take on a variety of shapes and sizes. Now, the basic concept of porosity, and indeed several important concepts describing porous materials, will require understanding this concept of the representative elementary volume, or what we'll call an REV. And to see how this works, we're going to look at this diagram on the left, and we've got some idealized grains here, and then there are voids here in between the grains. And the important thing to realize is that we've got two materials, grains and basically grains and not grains, grains and voids. And we need to describe this situation with just one number. That's the ratio of these two. And so the important concept here is that this ratio will depend on the area over which we average to determine the ratio. So, for example, let's say we have an area that we're going to average that's that's given here by this pink square. So that would be about 50% voids over the total averaging area. So that would give us a porosity that plotted here. If we go from 0 to 1, the porosity is about 50% for an REV size that's equal to that. That's just the size that I've shown here. But the situation then is that if we move that area then over to there, we have a much higher porosity because it's almost all pores. So that would be, say, 80% porosity. And if we move it to there, then there are no pores there. So the porosity would be 0. And we could move it around again. It's all in a pore, so it would be 100%. And so what we get then is that at this scale, at the scale of the pink box, the porosity ranges from 0 to 1. And so that's a consequence of the definition of porosity and the size. And what we get then is that that's not really all that useful as a way to describe this porous material, because it ranges over the full possible range of porosity. But if we take a somewhat bigger area, then we would get a porosity that plots there, and now we've increased in REV size here. So the REV size is increasing in that direction. And if we move that box around, then we get some a point that looks like that. It's got more pore space than the previous location, and we could move to another one that plots there, and so on. And we get a couple more points as we move around. But the situation is that as we now have a larger averaging area, we include basically grains and pores in no matter where we go. There are some grains and some pores. So we never really reach the extremes. We never reach 0 and 1, but the porosity still covers this span. So I think you can see where this is going. If we go and have now a larger area and move this around, then we still get some variability in the porosity as we move this block around, depending upon just what the configuration is like, but it's really much smaller range. And then we can go to a larger block yet. So if we have a larger block, something that, say, is this size, then we move that around and we're out here, and we really get very small amount of variability. And so what we get then is, conceptually, we kind of have this envelope like this. And so the porosity at this scale or less is variable, but once we reach a certain REV size, we have porosity that isn't really varying much. It has a pretty consistent value. And so over this range, once we get larger than that, then the porosity has a meaningful value. It has a single value that describes the ratio of the pores to the grains. Okay? So that's going to be important, because that'll allow us to describe this complicated pore space with just a single number as this ratio of volumes. Okay, and we'll find that that's the case with other ways of describing porous media using single representative values. So one thing, though, that I should point out, well, let's just take a look here. So this size, and it's kind of a transition region, and the transition region for the averaging area, it has to be probably at least 10 times or maybe 100 times larger than the grain size, right? If we're down and averaging at the size of the grains, then porosity doesn't really have a meaningful value. But if it's, say, 10 or 100 times the grain size, then it does. And so that gives you a rough idea of the scale. One thing, though, that we should point out is that often, if we were to take a look at this region and zoom out, this is part of often these are rounded sediment grains. So we might have these grains right here, and we've kind of zoomed in on that. But we might also have then another layer here of some fine grain material, some other different kind of material. And so as we get the REV size larger, we get into, we go from these discrete grains where the porosity is variable, and then we get it larger to a point where the porosity is roughly consistent. But as we go larger yet, then we might start averaging different materials, and so then at larger grains out here someplace, the porosity may drift yet again. And so we'll have, if we define the porosity at a certain value, then really what we're saying is that we have a certain range of size over which we're saying that the pore space or the porosity characterization is applicable. Okay, so that's the representative elementary volume, and it's important for porosity. It'll be important for hydraulic conductivity and some of the other properties of porous media. Okay, so primary porosity, this is the original void space, and there are many different ways that rocks form, and so there are many different geometries and types of primary porosity. Here's a carbonate rock, and so these are there's some kind of material, carbonate material from some kind of organism, and we see the primary porosity between them. Here's some clastic rocks, mostly quartz, and we have primary porosity between them. Here's some sandstone over here, and the porosity is stained blue. This is a photomicrograph, and this is the porosity between the pore spaces. But we'll see that in the case of sandstone like this, that this porosity has been changed from what it was when the sandstone was initially deposited. You can tell that because of these sutures between the grains. I'll show you more about that in just a second. Here's another case of primary porosity. These are vesicles in basalts. So that would be that would constitute the primary porosity. Okay, so medical imaging has come a long way, and the people who are interested in rocks and porosity have used it to take a look at what the geometry of pore space is like. So here are some examples from some sandstone with 22% porosity, and the pore space is being shown here. You can see there's a grain, there's a grain, there's a grain, there's a nice kind of circular grain, and then we have this pore space in between. It's 22% porosity, and you can see the pores are pretty well connected. But we fill the pores up or collapse them. There are a variety of things that will change the pore volume. And here's a case where the sandstone has only 7% porosity. And now what you get is that there are pores here that, like that one, that are just isolated. So those would hold fluid, but they wouldn't really contribute to the flow. And we also see there are some fairly large pores like this one. But if the fluid wanted to flow in this direction, you see that the pore space next down to, like right in there's a small choke point. So that would cause there to be quite a bit of resistance to flow. So the pore geometry is going to make an important, have an important effect on the amount of pores, amount of volume that you could store, and in particular the amount of volume that you could access, as well as the flow properties of the material. So here's another example of pore space that's been imaged with CT imaging, and you can see that this also shows some zones where the pores are isolated and would would constitute fluid that's included within the porous media, but probably is going to be difficult to have involved in flow processes because it's somewhat isolated. Okay, so porosity in limestone. Limestones are deposited in a variety of ways, but one important way, particularly with the Florida limestone, is deposition in the forms of reefs. And reefs are reef deposits are formed by organisms that form the reefs and form carbonate shells, and they can leave quite high porosities as a result. So this is a quarry here in Florida, and region about that size is blown up and shown here. So this is, I don't know, probably several tenths of a meter, maybe a foot or so across, and you can see that the pores here are quite large. They're visible. They're probably on the scale of a centimeter or so. Some of them, like right there, associated with these organisms that were these reef-dwelling organisms. So as a result of this, the porosity in this limestone will be fairly high, and also because these pores are quite large, the permeability will be quite large. Okay, so some controls on the magnitude of the primary porosity, how the grains are arranged relative to one another, their packing, their shape, and their size distribution. So the packing of grains, this is the relative arrangement of the grains, and we can see some end members. If we take some grains that are all the same size and all spherical, then one way that we could arrange them is shown here, and you can imagine that if this was 3D and they're rows like this, then this would be a packing where the grains are all lined up one on top of another. And with this type of packing, then the pores here are quite large, and the porosity you can calculate because if you assume that these are spheres and they have this geometric arrangement, you can calculate what the porosity is, and you get that it's 0.48 or 48% porosity. But you could also take these grains and shift them. So if you shifted this grain over to here, right there, and shifted this grain over a little bit, so it's right there, then the grain kind of falls down into the pocket formed by the grains underneath it, and you get something that looks like this. This is called rhombohedral packing, and you can also calculate the porosity for this, and it's 0.26. So if you just put grains and in a uniform size spherical grains and shake them and allow them to settle, then they'll tend to go towards this type of packing. So we might expect that. So you couldn't get the packing any less than this. So you couldn't have the porosity any less than this. This will be the optimal packing for spherical grains of all the same size. So I guess if we have well-sorted material that's spherical, we would expect the porosity to be somewhere between this and this. Now we'll never have something that's perfectly spherical and all the same grain size, but there are some sands that are quite well sorted and quite well rounded, and they would end up approximating this. And so we might expect then to have, I mean, this is actually quite a broad range, but what you often see is for clean, well-sorted sands, the porosity would be, say, in the 0.3 range, and it'd be bounded by these two extremes that are defined by the packing. So the grain shape will also play an important role. We saw what happens when you pack spheres, but mineral grains may also have different shapes. And here's a platy shape. This could be formed by micas or clays, and depending on how these grains are arranged, if you have something like what's shown here, you could have a very high pore space in relative to the volume. So this would be a very high porosity. And in fact, clays often are packed like this, where the edge of the clay is attracted to the surface. The edge of one clay is attracted to the surface of another one. So they often have arrangements like this, which cause them to have a very loose packing and very high porosities. And as a result of that, clays, which will be very small, they have very small grains, but they can have very high porosities because of how because of their shape and how this platy shape ends up packing relative to neighboring grains. So the high porosity of clays really is a result of both of these processes, the platy shape and the way that these platelets are packed together. Here's an example of quartz sand, and these are, you can see they're not really spheres, but a lot of them are quite close. And here's a photomicrograph of kaolinite, and you can see this plate-like structure in these kaolinites. You also take a look at the grain size. The clays, by definition, are smaller than 2 microns in diameter, and so that's actually, I'm not sure, that looks like it might be 10 microns, so that would make these about 10 microns, and yeah, that's pretty large. But anyway, in the micron range for the grain size. I'm not certain about that scale, but it certainly looks like it would be 10 microns. Okay, and here's the reason, or what I just said about the clay packing. Okay, so grain size distribution, this also plays a role in determining the porosity. A grain size distribution is the what relative fraction of different sizes of materials you have mixed together. If it's well sorted, then you would have something like this, all the same grain size. But if you have some large grains and some small grains, then you see how this would work. The small grains would be packed in the space that's between the large grains, and so the small grains then are filling up space that would otherwise be pore space. So if you have a grain size distribution with large grains and small grains, then generally the porosity will be smaller than if you have a grain size distribution that's well sorted with all the same grain sizes. So if you have poorly sorted material, you'll generally have less porosity. So there's an example of a well sorted sand, and there's an example of a more poorly sorted sand, where you've got large grains, medium, smaller, and smaller yet. So we'll describe the distribution of grain sizes using this grain size distribution plot. And the way you do it is you have a series of sieves. This would be a coarse sieve, medium sieve, and a fine sieve. And you put the porous material in here, and some material is retained on this sieve, some is on this sieve, and some is on that sieve. And then you go and weigh that, and then you can come up with a distribution of the sediment where a certain percentage of the material is finer than a particular grain size diameter that's defined by the coarseness of your sieve. So let's see, you would have then you have a series of points and you connect them with a line. So you might have several points like that and connect it with this line shown here as B, and that gives you the grain size distribution. Okay, so here's the way to read this, that if you have this B curve and you have this point right here, then that grain size, which would be, there's 0.1, so that would be 0.0987. So there's 0.07 millimeters, and 80% of the material is finer than 0.07 millimeters. But for B, this B grain size, we then go to right here, and that's 2, 3, 4, there's 0.04, that's 0.04, and only 10% is finer than 0.04 millimeters. Okay, so most of this material B is between 0.07 and 0.04 millimeters. Okay, that's actually quite well sorted. So that's a pretty small range of variability for that kind of material, for material B. And if we look at this now in material C, what we see is that that 80% of material C is finer than 0.02, but then we go down here and 25% is finer than, let's see, this would be 9876, 0.0006 millimeters. Okay, so soil C or sediment C has a much broader range of grain sizes than B does. So we say that C is more poorly sorted than B. So it's often going to be convenient to have a way of describing this degree of sorting. So the coefficient of uniformity is one way that this is done, and the coefficient of uniformity makes use of some characteristic grain sizes, D60 and D10. So D60 is the grain size that where 60% of the material is finer than that. So on this plot we go to 60% and we go down here. So that would be D60 for this material A. D10, 10% is finer than this, so it's going to be a finer material than D60. There's D10 for material A, and so you take the ratio of those two sizes, and that ratio will give you how wide that span is, and that's a measure of the uniformity of the material. And if that ratio is less than 4, we'll call it well sorted, and if it's greater than 6, we'll call it poorly sorted. Okay, so those are some issues related to the primary porosity. Secondary porosity is where the porosity has been modified since the rocks were formed. And there are a variety of ways that this can happen. The rock could become fractured and you could create pores that way. You can change the pore space by weathering. This is changing of the mineralogy. You can dissolve away some of the material and you can compact it. And so I'll show you about those examples. So here's weathering. This is a picture of a granite, and you can see that there are some feldspars there. The pink grains are feldspars, the black, that's mica, and then the gray is quartz. And when material like this is exposed to shallow depths, exposed to water, the feldspars, this material here, weather to clay, and so that causes a big change in the porosity, because this granite, the primary porosity in granite is about 1% or so. But when these minerals here, these feldspars, and also to some extent the micas, when those weather, they turn into clays. Clays have a high porosity. So the weathering process where you transform one mineral into another is a way to, usually it significantly increases the porosity. Another thing that can happen is dissolution. This occurs in limestone in a big way, and limestone, here's a block of limestone, and you can see these cavities in it. So you increase the size of pore space by dissolving away the limestone, and here it is in an extreme case where the pores are big enough to crawl around in. And if you've ever gone and explored caves, then you've been inside the pore space of the rock, and you can see here's a nice water-filled pore with these guys here for scale. Here's another dissolution feature in that carbonate that we saw that was formed by basically a reef deposit, and you can see that this area has been dissolved away, and it's a kind of a cavity with this rough-looking rock exposed here inside this rough, very fossiliferous rock exposed. Okay, so dissolution can increase the pore space. This happened a lot in limestone, as we show here. It can also happen, though, in the previous example, where you have weathering of that transforms minerals from one mineral to another. In that case, some of the materials can be lost. So when in this case, where we have weathering of the feldspars to clays, during that process, some components of the feldspars can be removed and dissolved out. So you don't have these big impressive cavities like we see here, but nevertheless you have an increase in the porosity because material is dissolved away and removed. So here's another way that you can alter the porosity, and this was shown earlier in a slide where I had it labeled as primary porosity. Really, this is a process that modifies the primary porosity by compaction and pressure solution. And what's going on here is if you've got grains like this of quartz or really any kind of mineral, and you've got grains like this, and those grains are in contact with other grains, then what happens is that at this point of contact, you have quite high stresses. And those stresses cause the rock, or cause the mineral right there at the contact point to be more soluble than it is elsewhere. And so what happens is that right here at this contact point, it dissolves away, and the material is removed, and sometimes it gets deposited elsewhere, but it gets removed, and then the grains are able to come closer together. And you end up then with grains that start off looking like this. So these grains are supposed to be just right in contact at point like this, and they get pushed together and they form these sutures. So you see how these grains are interlocking like that. That's because the stress has been increased. That causes dissolution. This is a process called pressure solution, and it causes the grains to come closer together. This causes the whole sediment pile to become compacted, and it causes the porosity to be reduced. So here's another example of a photomicrograph, and you can see that's really pretty impressive. Once you're kind of keyed in on this, you can see that all of these grains are sutured together. Okay, so this causes the porosity to be reduced, and what you see then is if you look at many sandstones and you plot the porosity as a function of depth, then this is a figure from this publication by Blatt that the porosity of sandstone is generally is decreasing with depth. So maybe up here at shallow depths in the up to 40%, but then as you get deeper, this process of pressure solution is causing the porosity to be reduced. And shales, in this figure anyway, somewhat less data on shales, but we see a decrease in the porosity of shales with depth as well. Okay, so those are all some controls on porosity, and what we end up with then is a set of some kind of typical ranges for porosity that we might expect. So for a well-sorted sand, somewhere in this range, and this is really determined by the packing, the different types of packing that we could have. The rhombohedral or cubic gives it's kind of bounding that range. Now, if we reduce the sorting, so we have more fine-grained material in there compared to the well-sorted sand, so poorly sorted sand, we would then reduce the range, or reduce the low end and the high end. So that would be a typical range for poorly sorted sand that we might expect. And of course, then we would expect it decreasing with depth. A lot of our applications will be, we could expect it decreasing with depth. I should point out, though, I guess, that in this range, that this is going from 1 to 6 kilometers. So this is quite important, this range of depths for the oil industry, but for hydrology, our applications will be up here at much shallower depth, although we may be working with rocks that have been buried to this depth and then uplifted. Okay, so moving on then, clays. Clays, this guy is going to have the highest porosity among these ones that we're looking at, and it's 0.4 to 0.6, and that's because clays will often have this kind of packing where the grains are edged to face of the plate. Crystalline rock, like a granite, it has some pores. It only has quite small pores, but it does have pores in between the grains that are forming the rock, and in the range of 0.01 or say this would be, say, tenths of a percent. So there's 1%, there's 1/10, and in that general range is generally what you see for crystalline rock. And this would be intact crystalline rock. And then if you fracture it and have some fractures that cut through, then you might increase it from 1% to 5%. But really, fractures, even though they're very important for flow, but fractures tend to be fairly narrow and fairly small volume, and if they're spaced reasonably far apart, then they don't really affect the porosity by all that much.